you are listening to me. Actually, I have uploaded one handwritten diagram in MS Team to clarify some questions that I made yesterday, but I'm not able to see that here. Can anybody help here? Because it's not visible. But if I open the
multiplexing.
yeah. Can you see this now?
Yes, sir. It is in the files.
That handwritten diagram, can you see?
Yes, sir.
Oh, that's very good. So that's what I did. So yesterday, at the very beginning, I asked a question that what is the purpose of modulation? What do we do in the name of modulation, right? So you can see now that uh, the baseband function is shown here. The baseband function, and in that you can see that there are users like first, second, and nth user, G1F, G2F, GNF. That's the spectrum of individual users, right? And everyone has the same spectrum, like all of our voice spectrum actually are same. So from bandwidth minus B to plus B, we are taking the two-sided spectrum, as you know. You can have one-sided spectrum, which is cos omega ct or sin omega ct, or you can have e to the power j omega ct plus e to the power minus j omega ct by 2. Then it becomes two-sided spectrum. So I have taken here two-sided spectrum. So your voice spectrum, suppose extends from, say, I'm talking in respect of any modulation like analog modulation. So minus B to plus B. And if I modulate by a carrier FC1, right hand side, then the spectrum shifts actually. It shifts from the origin, becomes from 0 to plus FC1 and minus FC1. Can you see that? Hello? Can you see that frequency translation?
Yes, sir.
You can see that, right? So now if I take another person's speech and I try to modulate with the frequency FC2, then the same spectrum shifts to FC2 and FC minus FC2. But they are not overlapping in the frequency domain. They are orthogonal in the frequency domain, not overlapping. Similarly, I can take the nth baseband BBN and I can modulate by FCN. Then they are again offset and moved or translated to FCN and minus FCN. Now you can take all the n signals and put them together, add them up, simply add them up, sum up. Then you get the spectrum of the multiplexing signal. You can see that multiplex signal. So n number of speeches now available together, and you can transmit through simultaneously. You can transmit over the same medium, be it radio, wireless, or any transmission lines like coaxial cables, etc., by using modulation and multiplexing. So that is the benefit of multiplexing, modulation and multiplexing, that you can now transmit all the signals which are occupying exactly the same spectrum but with non-overlapping multiplexing and transmit together over the same transmission line. So this is one of the important benefits of modulation. Another thing is that when you want to transmit through radio transmission, then the wavelength, the size of the dipole antenna or any antenna will be proportional to lambda. For a dipole, it should be typically lambda by 2, as I have shown here. Okay. Now, if the lambda is inversely proportional to f, C by f. So if a frequency is 10 kilohertz, then lambda becomes 3 into 10 to the power 8 meters per second by 10 to the power 4 hertz. And that becomes 3 into 10 to the power 4 meter, a huge, you can imagine that 30 kilometer antenna size, 30 kilometer, can you imagine? Whereas if you go for 10 gigahertz, the wavelength size becomes 3 centimeter, and then dipole would be actually half of that. So you can see the transmitter antenna size also comes down to a very practicable, realizable value. And similarly, and at the same time, through the same antenna or through the same transmission line, you can transmit all the signals together. Does it make clear? Hello, does it clear to you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you very much. So I will close it and I will go to the main slide. Please, if necessary, please note it down in your class note. so that you can, because we'll be towards the end of the semester, we'll have a lot of quiz type of questions, and this will help you. Okay. Now let us go to the now let us go to the slides. Can you see the slides now?
Yes, sir.
Okay, now let me do it in a different way. Okay, uh, different way so that I can.
Sir, you're not audible.
Sir, you're muted. Try to unmute yourself.
carrier synchronization is required. But before that, we'll assume that we have an ideal carrier at the receiver. We have got ideal clock at the receiver. Does it make clear to all of you? Or any other question? Please respond. Does it make clear? Okay. So now let me go to the next slide again. So let me erase this. Okay. So I have erased this. Now let's go to the next one. The next one I have already explained yesterday that you have got amplitude shift keying. You have got, this is the amplitude shift keying, this is phase shift keying, and this is frequency shift keying. And in all the cases, actually, you have a carrier which is basically projection of this, this phasor. Okay. This phasor actually is going like this, moving like this, and at any instant of time it has an amplitude, it has a phase, and which is a phase angle made with respect to the real axis, and it has a frequency. So any of the three actually can be changed and leading to amplitude, phase, and frequency shifting. Okay. So we will consider more details about how amplitude, phase, and frequencies are switched. Okay, let me clear this. Okay, so let's go here. So in this particular slide, you can see I have given some features of ASK, PSK, and FSK. Now, the source of information in your digital communication system.
Excuse me, sir.
Can you hear me?
Excuse me, sir.
Yes, please.
Sir, there is some confusion because multiple meetings have been started.
Okay.
So could you please paste the link of this meeting for our classmates so that they can join?
So what I'll do, I should log out and log in, something like that.
No, sir. You have to just paste the link of this meeting in the chat box, and then it will be visible to everyone.
So this link is not visible to you?
No, sir. Many people are not getting the link in which you are teaching because there are multiple meetings.
Oh, I see. But anyway, I am new to the Microsoft Meet, that's what I said yesterday. So let me see how I can get, because there is no link given to me at least. So I have just logged in and I have started talking. But if there is any link to that, all the teachers are not there, no teachers are there from your side. Okay, so can I call them and tell them? Can I call them and tell them?
Sir, I think the link has been shared in the chat box. Maybe they will join in now.
Okay. So they will join from there itself, right?
Yes, sir.
Okay. Because this is the first time I am doing online teaching, and that too I am used to Google Meet for other conferences and meetings. But MS Meet I have never used. But still I have explored certain things and trying to do. So should I go back to my lecture now or wait for some time?
Yes, sir. Fine now.
It shows 2 meetings now. What does it mean?
Sir, you initially created a meeting and left it due to some issues. And that meeting is still going on.
So what do I do? I mean, should I log out from one of the meetings? Something like that? There are 2
No,
issues.
sir, I'm not sure. That meeting will only end if all the people exit from it.
So let all the people exit. Can you give a notice that to everybody that let us Meeting ended 14 seconds. I'm really very confused here.
So they will join you continue.
Huh?
So they will join you continue.
I'll continue. Okay, let me see. I mean, there are many options here actually. There are some options where I cannot use the cursor, which I am using. And there are some where I can use the cursor. Now I have got with something where I don't have a cursor. So very peculiar thing is happening. They should have been here actually. Join conservation. Again, the same problem has come here, and then I had to automatically comes. Okay, so I hope now you can see all of you are there. All of your friends are able to see. Hello.
Yes, sir.
Okay. I think there is some delay, the latency in the conversation. When I talk, I think you are listening to it little after a couple of seconds, and the vice versa. And that's because of network latency, I think. Okay. So let me get back to the discussion. Important features of ASK, PSK, and FSK. Now, the source of information, as I said, it could be binary, like 1, 0, etc. But it could be also more than binary. It can have 4 levels, 4, like if you take 2 binary digits and combine it, it can have 4 possibilities, right? So what you do is you have 0, 0, 0, 1, 1, 0, 1, 1. So 4 possibilities are there, and you can call them 0, 1, 2, 3. So MRE messages or MRE symbols could be there. MRE is more than binary. In general, you can say that this is MRE. I will show you that how MRE is used, when MRE is used, and for what is the purpose of that, what are the challenges, and so on and so forth. We'll discuss about that. Another thing which I discussed yesterday, I repeat that for PSK and FSK, they have the constant envelope. You must have seen that in my last slide, that PSK and FSK, phase shift and frequency shift, their envelope does not change. Only the phase transitions take place or frequency transitions take place. Whereas in amplitude shift gain, amplitude changes because it's basically chopped to 0 value. So as a result, here the average power becomes less than the peak power, or instantaneous power. This is the instantaneous power. Average power is average over the entire time. Whereas here, the peak power and average power are one and the same. So it has got certain benefits. So the power amplification is easier for PSK and FSK signals with constant envelope, because you know that with constant envelope power amplifiers work better than the changing fluctuating signal levels, power levels. And the last point is ASK and FSK can employ coherent as well as non-coherent demodulation. If you look at this particular thing, coherent as well as non-coherent as well as coherent. But PSK must use coherent demodulation. Because PSK, the information lies in the phase, and the phase of the carrier should be tracked by the receiver. And the moment you want to track the phase of the signal, not the amplitude or frequency, then you have to be in phase with the signal if you want to know the phase. So PSK requires a local carrier waveform. It requires a local carrier waveform at the receiver, which needs to be coherent with the carrier used in generating the incoming carrier waveform. The carrier which has been used in the incoming carrier waveform in the transmitter, that has to be recreated, which will be coherent or in sync with the local carrier. The carrier, incoming carrier and the local carrier should be synchronized to each other to make the PSK demodulation successful. Is that clear?
Yes, sir.
Yes, sir.
Okay. So let's go to the. I am going little slowly because slowly we'll develop that interactive method, and we'll be able to exchange more effectively. So let's go for some definitions. Binary and MRE modulation schemes. In general, the messages of the symbols like MIs, okay, MIs. So messages or the symbols MIs will have multiple levels that is greater or equal to 2 corresponding to many signal waveforms during its signaling interval. Signaling interval is the interval during which you send a binary 1 or a binary 0, MRD1, MRD0, MRD2, MRD3, whatever. Because these are MIs actually. Now these, so what is happening that 0 or 1 or 2 or 3 are being converted into, mapped into a sinusoidal waveform with some different phases and different frequencies or different amplitudes, whatever. So if it's a binary signal, then the M1 and M2 are converted into S0 and S1, S0T and S1T. Okay, it may be like cos omega t and cos omega t plus pi. That is minus cos omega. So these are the two signals, two binary symbols you might get, right? But if you are going for MRE symbols, then there will be S0, S1 to S minus 1, M minus 1. And for binary symbols, the big interval is TD. Okay, but for MRE symbols, the symbol interval is TS, and that TS is bigger than TEV. As I told you earlier, that if you have, say, binary stream, see, fundamentally everything is binary. You are going to convert into MRE. So what will you do is, you take 2 bits into a symbol. A symbol will comprise of two successive bits, and therefore it can have 4 possible values, 0, 0, 0, 1, 1, 0, 1, 1. So 4 possible values will be there. So then N will be 2, and the symbol interval will be TS equal to 2 TB. So I can see now that M will be equal to 2 to the power N. That means if you take 2 bits at a time and each bit has got 2 values, then 2 to the power 2, M will become 4. In other words, N will become logarithmic 2 of M. So if N equal to 4, how many bits will require? You take log 2 of 4, then N will be 2. Right? So this is the example I am giving. 2 consecutive message bits, say 0 and 1, may be combined to form 4, that is N equal to 4 possible symbols, 0, 0, 0, 1, 1, 0 and 1, 1. And each one of the 4 symbols can be mapped to a unique waveform, like cos omega t plus phi 1, cos omega t plus phi 2, or cos omega t plus phi 3, or maybe A1 cos omega t, A2 cos omega t, A3 cos omega t, or A cos omega 1t, A cos omega 2t, A cos omega 3t, A cos omega 4t. So either frequency or phase or amplitude, or maybe a combination could be assigned to each symbol, like 0, 0, 0, 1, 1, 0, 1, 1, to make the digital modulation work in this way. So as I have said clearly that each one of the 4 symbols, can be mapped into a unique waveform with a symbol duration of Ts equal to N into Tv. That is equal to 2 Tv in this case, because we are considering only 2. N equal to 2 or N equal to 4 you are considering. The 4 symbols in our example, in this example, 4 symbols, as I said, may have 4 different amplitude, phase, frequency for ASK, PSK and FSK modulations. So is that clear to you? Does it make sense?
Yes, sir.
Very good, very good. So we are making progress, right?
Yes, sir.
But you ask your friends whether the initial slides that I described today at the very beginning, should we discuss again maybe at the end for them? Or can you tell them on my behalf, and if there is a question I can answer again in the next class? Something like that. I don't want to lose you, right? I don't want to lose you in the sense that I will be happy that if all of you get all that I say for you. Okay? Good. So now let us go for next slide, which is this is very simple. As I told you that MRE-PSK, as I said, it requires coherent modulation because its information lies in the phase. So how to demodulate QPSK, we will discuss at length actually. Many slides actually will have. QPSK is one of the very popular actually modulation schemes. And the example that I have just now given you was actually a QPSK when it is a phase modulation. You look at that. So 00011011 Okay, can you see that? Now here if each one has got different phase. Okay, say phi 1, phi 2, phi 3, phi 4 and so on. Then it will become a QPSK, quadrature phase shift scheme. That is, there are 4 phases for the 4 symbols. So it is QPSK. So this is the QPSK with n equal to 4, and therefore how many bits? For each symbol there will be 2 bits, because 2 bits make 4 symbols. Similarly, you can have MRE FSK. Okay, MRE FSK, you can have a coherent demodulation, you can also have coherent non-coherent demodulation. Why and how we'll discuss later. Okay, if you are interested to know exactly why, I can give you a small hint. That suppose you have a binary FSK. Okay, binary FSK if you have, so that means there are 2 frequencies which are coming, either cos omega 1t or cos omega 2t. So you know which one is coming. So what you can do is you can divide into 2 branches. In one branch is tuned to F1, another branch is tuned to F2. Okay, and then once you get F1 cos omega 1t, you can do similar thing as you have done in PSK, or you can do it in ASK. Like ASK is envelope detection. So we'll go to that in details later on. Similarly, there are other modulation schemes which is called MRE quadrature amplitude modulation. QAM. QAM is a very famous. All these modems that you are having, you will see most of them are using the QAM. QAM means you can have amplitude shifting as well as phase shifting. Okay, that means a symbol, suppose that you have got 32 symbols. So can you tell me how many bits I require for 32 symbols?
5.
5. 5, exactly. Very good. So this 5 bits, 5 bits and 32 symbols. Now, this 32 symbols doesn't mean that you have to have 32 phase points. You can divide it between amplitude and phase. You can have, say, for example, 4 levels of amplitude, and each level of amplitude can have, 8 phases. This is what is called phase constellation. That means if you look at the diagram, you will see that for there are 32 points, and each point has a unique value of combination of amplitude and phase. That is what is called quadrature amplitude modulation. Somebody also call it amplitude dash phase that shift king, APK. And it requires, of course, coherent demodulation. N could be like 8, 16, 32, 64, 128, 256, and so on and so forth. As much as you can afford to have a hardware, you can go for this kind of modulations. Okay. Very interesting thing is that I put a point here that when you go for MRE, even for QPSK, where n equal to 4, can you see that your symbol duration becomes larger because 2 bits are put together, and 2 bits are put together means 0, 0 is represented by 0 or a particular phase, 0, 1 by 1, 1, 0 by another, and 1, 1 by another. So, but each symbol occupies a time interval which is 2 of TV. So you can see the rate is decreased. The symbols per second becomes half of the bit rate. The symbol rates becomes half of the bit rate. So that means what? You are able to transmit information at a faster rate. Do you see that?
Yes, sir.
So you can within the same, basically your bandwidth has reduced. We'll see that later on. So it's a very important thing that when you are going for MRE transmission, you can pack more information into the same time duration. It's like you are a door, right? And side by side, 2 persons can go. So throughput of the door is 2 at a time. Now suppose you take somebody on your shoulder, both of them, then 4 can go. One more, then 3 and 3, 6 can go, and so on. So it's like packing the information. So you can, in MRE modulation, what you are doing is basically you are packing. But there is nothing is free lunch in this world actually. So once you do that, that phases are very close to each other, amplitudes are very close to each other because your power is limited. Power is limited. So distinguishing 4 power levels and 4 phase levels and so on becomes difficult in presence of noise. So in order to do that, you have to give more power. Amplitude has to be increased. Then you can, of course, conquer this particular issue. So this is what is called power and bandwidth exchange, which we'll talk later. Is that clear? This is a very important aspect which will come back in the next module. Do you get some feel about what I said?
Yes, sir.
Yes, sir.
Good, good. So let us go to the next slide. Well, this gives you a generic picture of communication system using digital modulation, the basic scheme. So you can see now there is a message source. Can you see that message source?
Yes, sir.
Yes.
You can see, and then you can have a signal transmission encoder. I'll tell you what is this. After that, you have got the modulator, that that APSK, FSK, ASK or QM, whatever you do with this. And for that, you need a carrier wave. That is cos omega ct or sin omega ct, whatever you need that. After that, you generate the modulated signal. And then there is a communication channel. Channel means basically transmission line or wireless channel, whatever. And when it comes to the receiver, some noise also gets into the system. Then you have a detector. Detector is nothing but demodulation, right? And then whatever you have done here, I'm going to come to this actually: signal transmission encoder and signal transmission decoder. See, this is an important module in any communication transmitter and receiver: signal transmission encoder. Do you know that, which will discuss later? So this is, as I said, message source can be binary and or MRE. Signal transmission encoder, actually encoding is done to compress the signal. So compress the signal, I'll give you an idea actually. Suppose you are sending a text, right? And the text has got, suppose maybe 10 pages or whatever, 100 pages. You will see that some of the alphabets are more likely to take place and some of the alphabets are very unlikely. Like Q, X, Z, these are rather unlikely. But E is the, did you know that E is the most likely letter in English alphabet? You can see the sentence, you just see the sentence, how many E's are there over here? Too many are there. Okay, so E has got the highest probability. Something like Q or Z, I have to see that exactly. So they have the least probability. So what people do is that if the E is the highest probability, you assign E only one bit. And if Z is the least probable message, give it some 4 or 5 bits or whatever. So what will happen on the average? Your total size will shrink. Did you get the point? The one is over again, you make it very short, symbolic kind of thing. And the one is coming once in a while, make it larger. Instead of giving everyone the same word length. Because each alphabet, each letter ABCD has to be given a 01 string, 0110, whatever. Now this string can be smaller or larger, longer, depending on its probability. The more it is likely, you make it smaller, and larger it is, make it more likely, less likely, you make it shorter, less likely make it longer, and more likely make it shorter. Then you see finally the overall number of bits that you are transmitting will be lesser. This we'll see when I go for the next module. So this is what is called transmission encoder. You are encoding the received bit sequence into such a thing that overall number of bits gets reduced, and therefore you become more efficient in transmitting signal. Because communication, there are two things. One is that you must be efficient thing, and then it should be retrieved correctly without error, or as minimum as possible. Error as minimum as possible. So as I said, that this particular block does this job, but there are two other encoders which are not shown here explicitly. They will also be here along with this encoder. They are called channel coder and line coder. Channel coder is that there is noise which will be seen in the receiver. So suppose you are transmitting a binary stream like 0, 1, 0, 1, 1, 0. Some of the ones or zeros will become zeros and ones, and you will be having error. So in order to decrease the error, you can encode the signal in it. It will just have almost the reverse process. Here, if there is a binary 0, I am giving you a very crude example. We'll talk about later. Suppose you are transmitting a 0, and there is a noise added to this, so it becomes 1, or there is a 1 you are transmitting and then there is a noise added, 1 becomes 0. So, but if you transmit instead of 1 0 3 zeros, all 3 zeros will become 1 is least likely. So if you want to add up, if you want to code against the channel noise, you have to have some redundancy. So you reduce the redundancy in source coding in the original source, and while doing the channel coding, which will fight against the channel noise, you can add some additional bits and make it more robust against the noise. So these two things go together. And there is another coding called line coding. The line coding means you code the signal in such a way that there are many transitions in the signal, many transitions, 1 0 1 0 like that. Like if you have 4 1s or 5 1s, you can replace it by a unique combination where there will be some zeros in between, and those combinations will never be used otherwise. So this is for line coding, and if there are more transitions in a signal, it is easier to recover the clock and carrier from the signal. Because transition is the key thing, actually, main thing which helps you to recover the clock. If there is no transition, physically you don't see any clock there. Okay, so these are the 3 codings that you really get to employ in a digital communication systems. One of them is source coding, where you compress the signal and then go for channel coding to fight the noise, and line coding to have recovery of clock and carrier easier. And then the modulator we have discussed at length. Modulator we have discussed at length that it can be ASK, PSK, FSK, and their variants. Okay. Now I have possibly said already this communication channel. The communication channel is the one, is not only the air or the transmission line. It's basically a journey from transmitter to the receiver until you have decided whether the bit is a 0 or a 1. So before that, in the receiver itself, some lot of noise actually are generated and added with them. So where that could be channel like wired or wired means cables, etc. Then radio or wireless, along with impairment. Impairment means signal will be lost, reduced, noise will be added. There could be interference also. That means other signals may come into your signal. And distortion, like if you have sent a pulse, the pulse can be spread like RC filtering effect. And once a pulse is spread, a binary 1, tail of a binary 1 will interfere with the binary 0. So 0 can be interpreted as 1. Suppose you have got a 1 and 0, suppose you have got a, like this is 1, right? And then this is 0. Then again 1 and then 0. Now if there is a dispersion, or as I said, distortion, signal may be like this and then go like this. So you can see now this 0 has got a trace of 1, and then if you sample the signal here, somewhere here, you will get close to 1 and you can make a mistake. So all these things are a part of communication channel, and we have to fight with them so that our communication system operates successfully. Is that clear?
Yes. Yes.
Yes, sir.
Yes, sir.
So detector is, as I told you, detector is basically nothing but demodulator. Okay, and all these diagrams you will mostly get from Hakin. You can study Hakin for the time being. Sometimes I will take 1 or 2 things from other books, and my own experience I will also insert here. And some notations mostly will be same, but some notations I will be forced to change because I am taking some things from the other books and their notations are different, and therefore I have to change the notation according to my own design. But that should not be a problem for you because I will be explaining the implications of all the notations. Okay. So as I said earlier, demodulator can be non-coherent for ASK or FSK, can be, but it can also use coherent. But coherent is applicable for all modulation schemes requiring carrier recovery, as I said. And then you have got signal transmission decoder. So it does whatever you have done in the coder, the reverse process of this will become the decoder. So this is all about the whole digital communication system, which I have not shown here that before this job is done, one has to recover the clock and one has to recover the carrier and then perform all these operations, which I will discuss later. So it will be as a subsystem created here, somewhere here, a box will be here. Okay, and that will receive signal from here. It will be tapped from here, and then it will go there. It will go there. Okay. So, the clock recovery, carrier recovery, clock recovery, frame synchronization, all will be done through this carrier and recovered clocks, recovered carrier, and it will support the whole carrier as a subsystem. The receiver. Okay, now I am going to the next slide, which is from here I start the mathematical part of the whole thing. Have you heard of complex envelope of modulated signal in your analog communication system?
Yes, sir.
You have. So, do you know the implication of complex envelope? Can you tell me something? I mean, it is there in the slide, my slide, but why complex envelope is important? Or how it helps us. Okay, let me explain. Okay, so my objective now here is to find out the power spectrum and various other features. So why power spectrum is important? Because I want to know the spectral spread of the signal. Because when you modulate the signal, then around the carrier you have a spectrum, and that spectrum has got a spectral spread. And if the spectral spread is large, then you cannot transmit many frequencies at a time. But if the spectral spread is narrow, then you can transmit many signals at a time, as I said in my first handwritten slide. And there also the spectrum is important for us to know, because there could be a interference between adjacent channels, adjacent carrier frequencies in a FDM system where frequency division multiplexing is being done. So the spectrum has to be clearly understood, and once if you want to know the spectrum and for various other purposes also, you need to know the envelope, complex envelope of the modulated signal. Now let us come to the this particular case where any modulated signal ST that I have written here, any modulated signal ST can be expressed as, you can see now, A, then Fi, and then theta. Right. That was, as I said to you earlier, that if a carrier is something like A cos omega t or A sin omega t or 2 pi ft, where there are three things. It has got an amplitude, it has got a frequency, and it has got an angle theta I. And any one of the three or all of them can be modified. Right. So you can say now that it can be, you can see that now this entire expression can be split into two parts. One is cos omega, cos theta I, cos 2 pi Fit, and sin theta I, sin theta 2 pi Fit. Now this cos component is called in-phase component, because you know that if you take a phasor, as I showed you in the very first slide or second slide, that's the in-phase component, and the amplitude of that is Ai cos theta I, as you can, if you break the trigonometric expression. Similarly, you have got A sin theta I and sin 2 pi Fit. So this I will call Ai cos theta, Ai cos theta I, that I will call as SIT, that is the in-phase component of the signal, and it should be AI. I have missed it out. Okay, so AI sin theta I is basically the SQT. So SIT and SQT are the coefficient, basically coefficients or the modulating coefficients or modulating factors of the in-phase component, in-phase carrier, and quadrature phase carrier. Cos 2 pi FCT is the in-phase carrier, and 90-degree offset is sin 2 pi FCT, and that is a quadrature phase carrier, 90-degree phase shift. So now if you take this, right, you can say that it is a real part of SIT into e to the power j pi 2 FCT. Because if you take SIT, SIT is basically ST is equal to S hat T is equal to SIT plus J SQT, which is the complex envelope of ST. Now if you take this and this, if you multiply and take the real part, you will be left out with this. Right? So the most important part is here that you have been able to factorize the modulating signal and the modulated carrier, the carrier, unmodulated carrier. So they have been completely separated into two independent factors. That's a big job actually, and this is only possible when you go to the exponential domain. Okay. And when you go to exponential mode, it is a single-sided spectrum. But real part when you take, basically it's e to the power j omega t plus e to the power minus j omega t by 2. So they have become two-sided spectrum, and amplitude becomes half and power becomes 1/4 with respect to the original signal. So now as I see that if I have a modulated signal, either the amplitude or the frequency or the phase or all three of them or any two of them will be varying with time from bit to bit, one bit to another, depending on how many MRE system, what AM you are using, and that can be split into in-phase and quantitative components. And this fellow is solely carrying the modulating part, and this is the carrier, in-phase carrier. This is also quadrature phase modulating part, and this is the quadrature carrier, and together it is like this. So this complex envelope is a very important concept, and we'll be using it later also. And SIT, S hat T, is carrying only the information bearing part within it, and you can see interestingly that its amplitude, phase, and phase are capturing everything, even if it is a frequency OBI, because if the frequencies change, so FC will become FC plus delta. So e to the power j delta T will come into the S hat T. So complex envelope has the capability, but otherwise if you go for the trigonometric representation, it's all mixed up, it's messed up totally. You cannot view what is the part that is responsible for representing my modulating signal, and what is the part is my carrier. You cannot do that in a trigonometric representation. Okay, so but for PSK things are very interesting. The PSK things become very simple, because what will happen, this theta will become 0 or pi, A will remain constant. So it's theta 0 or pi means it will come out as plus or minus. So you don't need a quadrature component, only with the in-phase component you can do away for PSK. Okay, but for FSK, you will need it. But QAM also you need it. Okay, so for ASK also only A will be changing. So maybe plus minus A or A 0 A, plus minus A and 0, or maybe A by 2, A by 3, things like that. So for ASK and PSK, you see that you can manage with the in-phase components, whereas for others you cannot go by only in-phase components. Like you do QPSK problem हो जाएगा, क्योंकि UPS A will remain same, F will remain same, but theta will keep on changing. Since theta will keep on changing, you will get cos theta, sin theta, both non-zero values of cos theta and sin theta will get. So in-phase component as well as quadrature phase components will be there. Okay, so complex envelope is a mine of information. There's lots of information out there. So that's what I have emphasized here. That in the green color bullet, by using complex envelope form, we can factor out the information bearing part of ST. Since SIT equal to S hat T equal to SIT plus JSQT would capture as a separate factor any phase frequency amplitude variation of the carrier, while the unperturbed carrier remains. Please mind my words. Unperturbed carrier remains as a separate factor as exponential j2 pi fc. So that is the physical significance of complex envelope. Are you okay with this?
Yes, sir.
Is it clear? Okay. Oh, is it like water or milk? How much clear it is? Water or milk? I mean, water is very transparent. You can see very clearly what is there on the other side. Milk is not. So milk is good for health, but here it is water, right?
Yes, clear as water.
Okay, carry on. So now we come to the power spectrum. The power spectrum, my camera has shifted. Oh. Okay. See, the point is that possibly you can see my body language, but I cannot see your body language. I cannot have eye contact with you. So that's something, it's a bidirectional, it's a unidirectional communication. So if you respond, then it becomes much easier for me. So that's why I'm at least making sure that I am visible to you. Okay, so the power spectrum. In power spectrum, we make use of the concept of complex envelope because, as you know, it is a complex envelope, which is multiplied the e to the power j pi 2 pi f c t. So that is what is actually changing the spectrum of the signal. If you take a simple cos or sine omega t before modulation, it is a single line, right? It's a line spectrum. It is not a continuous spectrum, spread spectrum. It is spectrum. Spectrum is not spread. It will be just a line. It will be just a line. It will be just a line, right? It will be just a line on positive side and on the negative side also. But when the moment you try to modulate, it will spread like this. It will spread like this. Okay. So this spectrum will spread because of this multiplication. Because as you know that when I multiply cos omega ct by any other frequency, lower frequency like cos omega mt, you get side bands omega c plus omega m and omega c minus omega m. And if you have a two-sided spectrum, you have minus omega c or minus fc plus fm and minus fc minus fm. That is what you are getting here. You can see here. This is the original. This is the original spectrum of the baseband signal, and after modulation it goes to two sides. Okay, it goes this way and it also goes this way. So it's very difficult to draw these lines with the mouse. It never comes perfectly. So please bear with me, right? So yeah. So we are trying to find out the baseband power spectrum, because if you know the baseband power spectrum, you can just shift to the FC and minus FC and you can get the overall spectrum. So baseband power spectrum is what? It's basically the spectrum of the complex envelope, right? Because complex envelope is the one which carries all the things about modulating signal, right? So if I find out the power spectral density or the spectrum of a modulated complex envelope, I can find out the overall modulated spectrum. Like this one, from this one to this one. Now SBF can be obtained. The SBF, that is the baseband spectrum, can be obtained as a Fourier transform of autocorrelation function of the baseband signal. Do you have any idea about this theorem? Autocorrelation and Fourier transform of that? Have you heard? Have you read it?
Yes, sir.
So what is the theorem? It is called? It is called Wiener-Khinchin theorem. Do you remember? WK theorem, Wiener-Khinchin theorem. So if you have a random signal you cannot take Fourier transform. If it is a deterministic signal, say pulse, a single pulse, then you can take Fourier transform and take the magnitude square and you can get the energy spectrum, spectral density. But if it's a random signal, how can you take Fourier transform? Because you cannot choose a time segment because it is varying with time. So what you do is you take shift by itself and then you generate the autocorrelation function. Autocorrelation function is always deterministic, it's not random. And it can be proved that if you take the Fourier transform of the autocorrelation function, you will get the power spectrum of the random signal. Right? So this is how you can find out the power spectrum. You take the SBF and from the SBF you try to find out the spectrum of the modulated signal. So that is what I describe here. The power spectral density SBF of a modulated signal can be obtained from the previous relation ST. That remember that I gave you this particular expression earlier using frequency translation of the baseband spectrum in the spectral domain. So what you do is you can see that actual signal spectrum will be 1/4 of SBF minus FC and SBF plus. Okay, do you appreciate this expression? That 1/4 factor? As I told you that if you take a signal and if you represent in the exponential domain, half goes to the positive frequency side, half goes to the negative frequency side. But if it is a spectral density, power spectral density, half will become 1/4. So that 1/4 factor is important for the power. And then you have got positive frequency you have a positive frequency and you have got a negative frequency. Okay. So therefore, if I know the SBF, I can write the complete spectrum of the modulated signal by multiplying 1/4 with the SBF minus FC and SBF. This is what is that? This is so. Sorry. Okay. So if you know the SBF, you can take this as a frequency shifted version here, and then you can generate this. You can generate this actual signal spectrum. Okay, so that is why I am saying that spread of SBF on both. You can see that spread of SBF on both sides of carrier frequency, FC or minus FC, will eventually decide the bandwidth of the modulated signal. Suppose you have been given a channel, radio channel, wireless channel, that you have got some bandwidth, say B or say, and in that how many signals can be transmitted will decide on what is the spread of the individual signal. So therefore, finding the spectral width is extremely important. Then comes another important thing called bandwidth efficiency. Okay, so that is the rho. Rho is RB by B. You must have read Nyquist theorem in your baseband module 2 or module 1. You must have read. So you can see now, if you have a channel bandwidth B, you can transmit at a rate RB. If it is a baseband signal, you can transmit at twice the bandwidth, right? So RB can be 2B. And if RB is bits per second and B is a bandwidth, RB by B is bits per second per hertz. And that is what is called bandwidth efficiency. If somebody can transmit at a larger rate, then you can say the efficiency is bigger, higher. Okay. So as I said, RB is the data rate bits per second and B is the hertz. So take the ratio as bits per second per hertz. So this is a very important concept which we'll use for our subsequent, yeah. I wanted to clean this. Just give me some time. So any question from this slide? This is a very important concept building slide. So if you have any questions, please feel free. And I think I have already crossed my time limit, so I can stop it here for today. Or
Yes, sir.
Because 6:20 is my limit, but actually we lost a lot of time while adjusting with that, and so 10 minutes ho gaya aise, so I took like this. And for those who have joined later, do you want me to go back to that particular slide and explain? I think it will be good for them. What is your opinion? I'll take maybe 5 minutes. Oli.
Sir, you had already explained that in the last class only.
Yeah, but is that clear? Because I have given you the diagram this time. Okay, so the friends who have come later, if they have any doubt about that, they can discuss with you, and we can further do that, right? So should we call it a day today?
Yes, sir.
Okay, sir.
Thank you, sir.
Okay, thank you very much for all listening to me.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks.